0.94 here. We get 0.94 here. And for this one is 72 times 7.5. Or 540. Now, in order to calculate the flexural stiffness, which is the same thing as the EI effective, we have to, in the basis, in the scheme of this table, which is the parallel axis theorem, is the summation of column 7 plus the summation of column 9. So the summation of column 7 so if we sum column 7, we have 2,363.5 plus 85.5 plus 1,121 plus 5,686.2, and that adds to 9,256. 9,256.2, and the other column, which is the sum of the inertias times E about their own centroids, is 256 plus 0.94 2 times plus 540 for a total of 797.88. 797.9, let's say. So adding to that 9,256.2 gives us 10,054. 10,054. Yeah, 10,054, but of course, times, right, times what? All this calculation, column 7 times column 4, times normalizing E, right? Normalizing E. So, again, I remind you, when I started, instead of putting the actual E's, I put 1 instead of 4,000 and 7.5 in order to keep this number smaller. Had we used the actual numbers, 4,000 and 30,000, everything would have been 4,000 times bigger. Okay? Therefore, what we have is that this goes times 4,000, and so the flexural stiffness is that times 4,000. Why did it change it? Let's see. No, I don't like it. Wait. 10,000 and 54. MATLAB just changed its format on me. For reasons undetermined. But anyway, it's 40.21 times 10 to the 6. And because we're using kips and inches, it turns out that the flexural stiffness is kip inches squared. You can convince yourself that that is the case, that the units are that. Okay? So 40.21 times 10 to the 6. All right, so you have the table, you can see it. there could have been 3 materials, there could have been 10 materials, it doesn't really matter, right? You just have to list your areas, your modulus of elasticity, either in relative terms or not, and then do this to locate your centroid by dividing column 5 by column 3, column 5 by column 3, right? And then calculate your flexural stiffness by adding column 7 and column 9, and then multiplying by the relative value in case you kept it. Now, at this point, all I need is really the flexural stiffness, which we know that it is equal to 40.21 times 10 to the 6 cubic inches squared. So okay, so that's the flexural stiffness, 40.21 times 10 to the 6. Now, what is the curvature? Once we know, we went from loads to moments. Now, from moment to curvature, we simply go by dividing the moment, which was 900, but it was 900 kip feet. So that means that it's 900 times 12 kip inches, divided by the flexural stiffness, which is 40.21 times 10 to the 6 kips inches squared, and we see that we get an inches to the minus 1. So we get 900 times 12 divided by the answer, and that is equal to, let's see, I don't know why this thing decided to change the format on me. I believe it's 2.6855 times 10 to the minus 4 inches to the minus 1. Let me double check. 40.21 times 10 to the 6 divided, no, that's 900 times 12 divided by that. .68 times 10 to the minus 4. Okay, so that seems to be correct. 2.68 times 10 to the minus 4 inches to the minus 1. So 2.6855 divided by 1, 2, 3, 4. 1 divided by that. And that divided by 12. Just for curiosity, we can calculate rho. We don't really need it in our calculations, but we can calculate rho, which is 1 over the curvature in inches, and then convert it to feet, and we get 310 feet. So that means that in this beam, okay, when we put the loading and the beam deforms, at this point, which is what the curvature is biggest, if we wanted to know how curved it is, the compass opening would have a radii of 310 feet. Okay? All right. Now that we have the curvature, then we can go and say, where is it that you want to know the stresses? You wanted to know it at point A? Okay, so let's look at point A. At point A, what is the strain at point A? Well, it's the curvature, which is 2.6855 times 10 to the minus 4, times how far is it, because remember the curvature is the strain plot, goes through here. We want to know the strain there. It's the curvature times how far it is. And how far is it? 5.51 inches. And so we find that 2.6855 2.865 times 50, that's E, times 5.51 is 0014. Okay, so 0014.8. So that is the strain at point A. So the stress at point A is equal to the strain at point A, which is 00148, times what modulus of elasticity? Well, where is point A? It's in the concrete. Therefore, times the modulus of elasticity of the concrete, which is 4,000. And so we find that the stress is equal to 5.92 kips per square inch. Okay? Let's see, 148. Okay? 5.92 KSA. That's what we're getting. Under the assumptions, of course, of linearity and so on. It may be that the material cannot take that stress, so that doesn't mean that that's really the stress there. That just simply means under the assumptions that we've made, that is that the materials are behaving elastically with this modulus of elasticity, if they were to resist those loads, they would actually develop a stress that big. We might actually conclude that our concrete is not capable of remaining linearly elastic for that high stress and so on, and then we'd have to make a change, but that's not our point at this location. Now, I haven't made any emphasis on signs, but the moment that has been applied here is the moment, excuse me, I'm getting a call, let me cancel this, this telephone call. Hello? I am taping a lecture. Bye. So we have that the stress at point A is 5.92 KSI. Now, if we, the moment that we have is of this nature, right? So the beam is bending like this. At that point, you can see that compression is on the top. That is, there is compression above the neutral axis. Therefore, that is a compressive strain. Now, you can call it minus, or to be more clear, you can just say that that's a compressive stress, right? Now, if we now go to point B, point B was, if I believe correctly, down here at the bottom corner. So we have the curvature, and the distance to point B would be the total of 1/2 inch, no, I'm sorry, 4 plus 1/2 is 4.5 plus 12 is 16.5 plus 1/2 is 17. So we'd have 17 minus 551. So the distance from the neutral axis to point B is that much, and therefore we find that that strain is equal to .00309. And so we have that the stress is equal to the strain times the modulus of elasticity at the point that you're doing the computation. So this is a steel point, therefore that is 30,000. And so times 30,000 is 92.57. Gibbs per square inch, which is a value that is too large. We would have to actually increase the size of this beam. That stress is too high. You know, the stresses that we can normally accept on steel beams under loads like that would be on the order of 20, 25 at the most, something like that. So basically KSI. So we've got maybe, you know, a beam that is too small or loads that are 4 times too large, or a span, whatever is it that you need to do to reduce that moment. Or another way to say it is that the moment that we can really take is not really 900, but something more on the order of a quarter of that. Okay, so that this stresses would go down. So that this stress would go down to about a quarter of that. Now finally, point C was here. And so point C, which is in the steel, but in the steel section, but here the distance would be 5.51 minus 4, right? And so that's 1.51. Or 0000405. So the strain in the steel at point C is 0000405, and the stress is how big? Well, it's in the previous one I should have written tension because it's down here, right? So it's compression above, tension below. This point is also compression. And it's this number, I'm sorry, it's a double, what did I got? Calculate, 0000405 multiplied times the modular elasticity of steel, which is 30,000. And we get 12.17. Okay? And that's it. So this example illustrates to you the procedure of how we compute, how we pass from loads to stresses, to bending stresses, in beams whose cross sections contain more than one material. Now, without numbers, I want to close by just simply saying, if the section was like this, right, we have to determine the principal axis, right? And up to this point in the class, the only way that you can calculate the principal axis is in the case where there is at least one axis of symmetry, so that be more precise. Imagine that I drew this thing and it's symmetrical, you know, this way or something about this line. So if this is an axis of symmetry, that's a principal axis. Now, the section may not be symmetrical about the other axis. The other principal axis is necessarily perpendicular to this one, but where it is, we don't know. So now if the section happened to be symmetrical also in this direction, then we'd be all set, because we would already know where it is and we don't have to do part of the table. But in general we don't, and so we have to locate it. Notice also that when we talk about symmetry, that doesn't mean symmetry in geometry only. For example, if I gave you this section, okay, and this section had 1 inch here of steel and 1 inch here of aluminum, okay, and this is wood, for example. So we have steel, wood, aluminum. That means this has one modulus of elasticity E1, this has another modulus of elasticity E2, this has another modulus of elasticity E3. Is this section symmetrical about this axis? Yes, it is. Because about this axis, everything is the same on that side and on this side. But is it symmetrical about the middle here? No, because the geometry may be the same, but this is steel and this is aluminum. So we again do not know where this axis is and must be calculated. Okay? Now, once we calculate where our axis is, y bar here, you know, this could be, I don't know, something made of, this could be material E1 outside, this could be material E2, and this could be material E3. And by the way, if this was a hole with air, you can still think about it as being a material with E0, right? Now, once you have that situation, you do your table, and you have your y bar, and you have your flexural stiffness, right? Once you have your flexural stiffness, the process is very systematic. You take your moment, you divide it by your flexural stiffness, and that is your curvature. And once you know the curvature, you multiply the curvature times your distance to whatever you're interested in, and that's your strain. And once you have your strain, you multiply times the modulus of elasticity at the point of interest, and you have your stress. And that's it, okay? So check the web in Blackboard with regards to homeworks, okay?